Today's two keynote talks, and I'm very happy to welcome YEJIN CHOI and as a second talk, ESTEVAM HRUSCHKA. The topic of today's two keynote talks is common sense reasoning. In my view, and not just in my view, this is the topic of the future. It's a topic where AI certainly goes pretty strongly in the last 2-3 years, especially with significant DARPA funding. But as I see also, many companies are investing in this area, although the problem is maybe one of the hardest in AI. This is one of these AI dreams, right? So somehow the deep text understanding to beyond counting the words, beyond embeddings, beyond eigenvectors and so on, what we usually do in text mining and computational linguistics and so on. Okay, we do a few more things, but certainly deep text understanding is not a topic which we reached very far so far. So common sense reasoning has a long history from late 70s, early 80s, with Psych as being one of very prominent experiments, which is still around. But in the recent years, there were a few new approaches, and YEJIN is maybe one of the main promoters of these new approaches with very successful results. That's why we invited her. So today's talks will complement each other. So YEJIN's talk will be more from the academic side, and the second talk by ESTEVAM will be more like on the industrial side, how this common sense reasoning techniques are being applied in the actual results, right? So a few words about YEJIN. I heard a couple of her talks in the last year and a half, and I was always learned something, right? Just a few words. So YEJIN is Brett Halsell Associate Professor at the Paul Allen Institute and at the University of Washington. Also senior research manager at AI2, overseeing the project Mosaic, which I think will be described today. She has broad AI research interests, including, of course, common sense, knowledge, reasoning, neural language, language grounding, and AI for social good. She got many awards, including she was on a IEEE AI Top 10 to watch back in 2015. So I guess it was justified. YEJIN, please start.
Okay, thank you so much for having me here, and thank you for the very thoughtful introduction, Marco. I'm so honored to share our recent adventure for pursuing common sense AI. So why do we care? Well, because despite human level or even superhuman level performances on leaderboards, today's SOTA models are brittle if given adversarial or out-of-domain examples, making such silly mistakes that humans would never make. So as if today we know how to solve only a data set without solving the underlying task. So why are we not able to do systematic generalization? When people think about that question, well, fundamentally, there's a major difference between how humans learn about how the world works and how today's best neural models learn data set specific patterns without really reconstructing the knowledge that we know about the physical and the social world. So when people think about that major difference between human intelligence and machine intelligence, we often think about this system 1 and system 2 reasoning. So this notion became better known due to this book, Thinking Fast and Slow by Daniel Kahneman, the Nobel Prize winner, which is good. I mean, the fact that we think about human cognition is a good thing, but unfortunate myth that seems to float around the community is that we know how to do system 1 reasoning now with deep learning, and we only need to figure out system 2 reasoning. I will dare say that that's a major misunderstanding, especially in light of Kahneman's work. In fact, in his earlier work, the academic paper, not the book, he emphasized the 3 cognitive systems that has perception layer under the system 1 intuition and system 2 reasoning. And perception and intuition together correspond to the fast and automatic effortless associative reasoning. And then system 2 is the one that we know as slow, effortful, and more logic-like. And then, interestingly, there's also a lot of shared commonality between system 1 and system 2. These 2 things are not as clean-cut different things as we may have assumed. So both of them share the needs for conceptual representations, the needs for reasoning about past, present, future, so causal and temporal reasoning. And then also they both involve language quite closely. And so when we think about system 2 reasoning, we typically associate that part with solving puzzles or writing programs or proving logic theorems. But it's not just that, it's also about reviewing WebConf papers or giving an invited talk, writing an op-ed. So all of these acts do require a fair amount of focus. Compared to perception, of course, we do this pretty much unconsciously, seeing objects and also hearing speech. And in between lies this really interesting layer of cognition, intuition. And so this is inferences on preconditions and post-conditions, what happens before and after, reasoning about people's motivations and intent and their mental and emotional states. Again, we do this unconsciously. We do this pretty much every waking minute of our life. Compared to reasoning 2, a lot of people don't need to do this in order to have a day-to-day, just a simple life activities. So to make this talk is going to be really focusing on this intuition. And to make my point clearer, let's look at this example, Roger Shepard's Monsters in a Tunnel. I first saw this example in a keynote given by Fei Li at NACL 2015. It's a really enlightening example where it demonstrates how it's not enough to just be able to say there are 2 monsters in a tunnel. We see a story around it, that 2 monsters are running as opposed to standing still on one foot. One is chasing another, as opposed to trying to copy his body movement or their body movements. The chaser has hostile intentions and the chased is afraid, even though 2 faces are identical. And the actual textual examples are taken from this book, The Enigma of Reason, that inspired this content of this talk as well. So important observations here is that none of these inferences is absolutely true, in that the inferences are stochastic in nature, and then everything is divisible with additional context. And a great deal of intuitive inferences, as demonstrated here, are common sense inferences, and they can be best described in natural language. Full scope of language, not just words or sets of words or graphs of words. When we think about inferences, it's very easy for us to think about just some categories, variables that people define. So when people think about symbols, they tend to think just the words or numbers, but in fact, that's not enough. We do need to incorporate the entirety of language as symbols. And similar point is also the key idea behind these surfaces and essences by Hofstadter and Sander. You might recognize the first author's name from another book that's probably more famous, Gödel, Escher, Bach. But this book I highly recommend. Please take a look. And in this book, categories, the author is one of the thesis of the book is that the concept categories vastly outnumber words and require free-form open text descriptions. And so there are these compositional concepts that require free-form text descriptions, and they're a little bit symbolic in some sense, conceptually, but we don't need to invent every single new variable for them, and we can just use open text descriptions. And if you buy that, then reasoning really becomes generative tasks. So the moment we buy open text descriptions as the necessary aspect of broad scope common sense reasoning. And by the way, even for this monster in a tunnel examples, when we reason about what they're doing, why they're doing, we needed some open text descriptions. We couldn't just categorize them into some predefined perfect subset of categories that someone else defined. There's no such a fixed set ontology. So we cannot do discriminative tasks or categorization anymore, because the space of reasoning in language is infinite. And so even if we somehow pare that down to 1 million categories to choose from, it's going to be very slow to enumerate all of them one by one. In fact, when we thought about these monsters in a tunnel example, what they're doing, probably the answer comes to your mind without imagining the alternatives. Like, are they sleeping? Probably doesn't even come to your mind. And so the fascinating thing about human reasoning is that we can reason as we speak on the fly, word by word, without enumerating all possible alternative sentences. So I think this is one of the really exciting research direction to give a serious thought into. When we think about reasoning, we oftentimes try to detach it from language and then try to define categorical symbols, but maybe we should operate directly with language. So in this talk, I'm going to explore that idea as reasoning as a generation. And the first part of this talk, I'm going to describe some unsupervised inference time algorithms in order to make lemonades from off-the-shelf neural language models that are not able to do this kind of a reasoning reliably. So and then the second part will be about common sense knowledge, and I'll share some closing remarks. So the first part is going to be Delorean. And before I begin what this work is about, let me highlight the fact that when we think about reasoning, we oftentimes think about induction and deduction. But in fact, what humans do are much broader than that. So we do abduction, for example, and this is reasoning about why something might have happened, or reasoning about the best explanation to partial observations. This notion was first described by Peirce. He was American philosopher, logician, mathematician, and he's also known as the father of pragmatism. So this abduction or abductive reasoning has a close connection to pragmatic understanding of language that's essential for our common sense reasoning in language. So another important aspect of reasoning is counterfactual reasoning, and this probably is what everyone knows about, what if. Reasoning about what ifs. So I'm going to focus on this later too, because these are less studied in the field, especially involving language. So there's this data set that we're going to work with, which has 2 sentences as an input, past observation and future observation. So for example, if in the past, Ray hung a tire on a rope to make his daughter a swing, and then soon after, he ran to his daughter to make sure she was okay. As a human, we can reason or imagine what might have happened in between. Probably some sort of accident happened. So we don't know for sure what exactly might have happened. But for example, it may be that she hit the rope and the tire fell on top of her. And so that's an example of abduction. And we do this all the time. And counterfactual reasoning, for that, I'm going to use this example from dataset Time Travel, and it has 5-line stories. So here, Zach was throwing a party. All his friends were dressing up for the Halloween party and considering to be a vampire or wizard and so forth. But what if we change the second line of the story so that it's a different counterfactual context? So instead of any Halloween party, what if it's a Game of Thrones themed party? In which case, we want to revise what follows next a little bit so that it's more consistent with new counterfactual context. And as a human, we can do this quite easily. You don't need to fine-tune or to supervise the training in order to be able to do this on tens of thousands of examples. You can just go ahead and do it right away. And so this is our model output that I'm going to describe in a bit. And it's able to change the rest of the story to say, oh, Zach thought about being a Lannister, but didn't look like a Lannister, so decided to dress up like a Stark. It's a pretty good one if you know the TV show. And what's you might wonder what might be the commonality between abductive reasoning and counterfactual reasoning, because they may seem very different, but there's the common aspect of these two tasks is that they both involve non-monotonic reasoning and also involve reasoning about the past context and future context in order to produce some output. And so doing this using pre-trained language models for text generation is quite awkward, especially GPT-2 or GPT-3 that generates language monotonically from left to right. Such language models are good incorporating the past context, but it's quite awkward what to do with the future context. Either it's not going to look at it, or we might try to put together past and future into the past using some special symbols in between, and then try to fine-tune the pre-trained model on a lot of data in the hope that something nice happens in the end. And such method is the standard right now, and it does tend to improve quite a bit, but it's not going to generalize well on new domain. And also the fact that we always have to do the supervised training, or these days called as a fine-tuning, is not a good thing efficiency-wise. And also, as a human, we never really need to train ourselves to read text out of order and then try to guess which sentence might be missing in between two sentences. So we don't need to train ourselves, and yet we are able to do such revision of text or generation of a missing sentence in between without any fine-tuning. So the hypothesis here is that maybe it's possible to do it, and in this work we're going to achieve it through backpropagation, which is usually training time algorithm, but can be used for inference as well. And in fact, such idea has been already used by image style transfer, where the style loss was backpropagated all the way down to the input image to change its style. And so here, the network parameter is already fixed, and backprop is used only as an inference time algorithm. So in this work, we're going to explore that. It's not as straightforward as the image case, though, because language is discrete. Now, I'm going to give you just a visual sketch of our algorithm Delorean, which is a time machine, and we can progress faster than real time, just to get you the intuition without getting into details too much. But so we do the usual business of computing the embeddings of sentences. So given X and Z as past and future, we are going to generate or reason about what should come in between. And after computing Y and Z, we can then compute loss function, which is conditional probability of the future given the past, and so that we can do backpropagation down to the intermediate representation Y. And like any other backpropagation during training, we also do this through multiple iterations, iterating between forward pass and the backward pass. And then eventually we do need to change this continuous representation to some discrete words. So what you see here was the examples that we saw earlier in the talk are the actual model output from this Delorean algorithm. And then for counterfactual reasoning, which looked like quite a different task, in fact, we can use the same algorithm. So here we use KL divergence between the original story ending and the new story ending. And other than that, we use the same algorithm. And to our surprise, the model, sometimes when it does work, it's quite surprisingly good. And so in terms of evaluation, though, currently there's no way to do automatic evaluation in a reliable way. So human evaluation is the standard. Here, the higher is the better, and human performance is the best, which is the yellow. And our Delorean is able to do better than supervised model strengthened with Comet, the neural common sense model that I'm going to talk about later in the talk. So that's very encouraging. However, the gap between human performance and machine performance is very large. And this is actually an important point of neural networks today. When they seem like they're achieving human level performance, it's almost always the case that it's evaluated on multiple choice questions, not generative evaluation. So I'm going to go back to that point in a bit. But let me give you another such example, neural logic decoding. So this is for controlled text generation. And the standard recipe for controlled or conditional text generation today is to use sequence-to-sequence models. And the example applications include machine translation, dialogues, and image captioning. And then here I'm going to introduce you a new fun task called the Commongen. And it's a common sense generation task. And the task is to write down any sentence that's reasonable using all the words provided as an input. So as a human, this is super easy task. You don't need a even single example to fine-tune your language model on. You can just go ahead and do right away. But neural networks today, they don't learn this type of logical constraints as well. Here's another example, machine translation. So oftentimes it makes certain grammar mistakes, especially gender-related inflection, changing the gender through this translation. And this happens because the neural translation is relying too much on the statistical patterns instead of really truly learning the grammar rules, which have a little bit more logical flavor. So in this work, we explore a decoding time algorithm called the neural logic that takes logical constraints in CNF form or conjunctive normal form, which is a combination of the clauses CI through conjunctions, and then each clause has literals inside, which are disjunctions of literals, which can be either positive literal or negative literal. In this work, we assume that all these literals are some word items that either should be included or not included. And so we design an advanced discrete search algorithm that can search diverse partial solutions of that conjunctive normal forms in consideration of the dynamic state changes of clauses, because they can be flipped between satisfaction state and unsatisfied state depending on what sort of literals are inside. So it's a little bit involving, but I'm going to just skip that part over and just show you the final result. So this is conventional method, so fine-tuned language model, supervised models using conventional beam search or the newer nucleus sampling. That's one of the sampling method used in NLP field lately. And they both all of them make some mistakes. They all learn some patterns to make some use of the input words, but it's not able to use all of them. Whereas with neural logic, everything is being used. What's exciting is that this still works with, the neural logic still works with off-the-shelf unsupervised models, just the same as before. Whereas, of course, untrained only pre-trained but not fine-tuned models cannot do anything sensible at all. And so in terms of the final performance, when we look at the coverage, so neural logic on top of supervised model and unsupervised models are green and yellow. And then blue is the conventional supervised model with the beam search. And then the x-axis shows the size of the model. And so we see that the blue line shows that the larger model does better. That's almost always the case these days. And this is still true here. But with neural logic decoding, it actually doesn't matter. The model size doesn't matter. Supervision doesn't matter. The percentage of constraint satisfaction is almost 100% always. And one might wonder whether we achieve it by giving up on the generation quality, which are in this task, which are correlated with the Rouge and Meteor, which are some n-gram-based statistics, as shown here. And higher is the better, again. And as we see, neural logic just outperforms supervised model, whether neural logic is used on top of supervised or off-the-shelf zero-shot models. And what's more remarkable is that neural logic wins over beam search supervised version, even using smaller network. Even using smaller network, we can do better than larger network. So the common theme these days with deep learning has been that the larger the better, just make it as large as possible. But we might have forgotten that algorithm can do so much in computer science, and it can actually draw the best out of neural models, especially when they perform very well. Increasing size is one way to do it, but adding algorithm might be another way without necessarily burning too many GPUs, which is not the most environmental friendly way of doing science. So to comment a little bit more about that, so current paradigm of deep learning, especially for a lot of NLP and computer vision leaderboards, has been to do supervision on a lot of exam problems on top of self-supervised or pre-trained model. But this recipe fails miserably on generative evaluations, as we've seen so far, such as abductive reasoning, counterfactual story revision, and various constrained text generation tasks that require logical constraints. By the way, the neural logic decoding that I presented, the paper has 3 additional applications with similar empirical results, which demonstrate that this current recipe of doing deep learning does work really well for certain types of leaderboards, but not all types of AI problems. And why would that be is, I think it's a little bit similar to human learning. So imagine taking a deep learning class in which professor comes in, there's no lecture, and just like supervision provided based on a lot of QA problems with correct answer marked. And there's no lecture, no textbook. And so students probably will not be very happy learning this way. So then the professor says, oh, that's because we got to do self-supervised learning without supervision on a lot of raw data. So provides you with a lot of deep learning code. And some of you might think, oh, I know how to read the Python code. But what if the code is written in, I don't know, Korean language and it's new program language, and you have to learn the concept by predicting which word is missing in between? I don't think we can, even as a human with powerful intelligence, we cannot learn concepts well enough this way. We really need to see some sort of a tutorial or lectures or textbooks in order to learn efficiently. So humans really are capable of learning things from declarative knowledge descriptions. And the problem with this supervised training is, of course, there's always this exam writer's biases baked into this multiple choice design, which creates the machine to pretend that it's doing really well on a data set without actually solving the underlying task quite reliably. So that motivates the second part of this talk, which will be about knowledge modeling. So it starts with the Comet 2020 or Atomic 2020, which is the better version of our previous work, Atomic and Comet, which correspond to the symbolic and the neural common sense models. So in this talk, I'm going to just merge all these three papers into one combined story. And the main thesis here is that language models off the shelf are not knowledge models, and we have to think about knowledge models more carefully instead of just relying on pre-trained language models as is. So atomic knowledge graph is a symbolic knowledge graph that has everything that used to be in the original atomic knowledge graph, which included inferences like if X gets X's car repaired. So given the center event, we can reason about a lot of preconditions and post conditions. So for example, X might then call Uber for a ride or pay the bill, might need to find a mechanic and money. Oh, by the way, money can be used for paying repairs, or we can also fold that into origami if you want it. So the new Atomic 2020 has a lot of new knowledge about stereotypical use cases of objects or affordances of objects. And then we also have this fun new relation called hindered by. And this is basically a counterfactual situation in which the center event cannot happen. So you cannot get your car repaired if the car is totaled completely, and so forth. So we have in total at this point, this is all entirely crowdsourced, by the way. We have a 1.3 million common sense if-then inference rules, all written in natural languages, and then over 23 inference types. So the paper provides a lot of evaluation, but let me highlight just one evaluation, which probably is the question that everybody has these days. How does X compares to GPT-3, whatever X is? So here, to give you a little bit of perspective, by the way, GPT-3 is more than 400 times larger than our Comet model. I forgot to mention, Comet is common sense transformers trained on the atomic symbolic knowledge graph, and it's originally pre-trained on language. So it's a language model-like object that's further tuned on atomic knowledge graph. So it's almost as if language models reading some common sense textbook, which is atomic, and then learned about a lot of common sense knowledge. So it's more than 400 times smaller because it's built on a language model called the BART. And with that in mind, GPT-3 performance is quite shockingly good. So here, the higher is better. And these are tested for a little bit adversarially for Comet in the sense that we split the test set to be as different as possible from the training set. And so Comet performance usually is better if you do random split. But in this setting, Comet is the best, but GPT-3 is shockingly good, especially in comparison to GPT-2. But of course, we cannot download GPT-3 to anybody's machine. In fact, it's not even available. The API is not necessarily available for everybody. So if you want a smaller model that performs better, then I recommend the Comet. So Comet generalized much better on out-of-domain examples than we realized at the time of our first paper publication. So you can go here, demo site, and then if you click atomic portion, you can run the Comet demo built on top of atomic. But we also have another common sense, very famous common sense knowledge graph called the ConceptNet, which we also trained the Comet on. So you can play with that version instead if that's what you like to play with. And the way it works is that you can just write any text like John gets into an accident. Instead of writing person X gets into an accident. So atomic knowledge graph doesn't have a people name. It's all about person X, person Y. But Comet generalized quite well, even if you give natural language prompt like this. And the inference is quite exciting that, as a result, maybe person X wants to call 911 or get medical attention, even though these words do not even appear in the input description that John gets into an accident. there's interesting level of abstraction happening as well. So if you go to this tab called Atomic under Knowledge Graph, you can then search what is in the atomic knowledge graph. And the best way to search it is to type one content word, like conscious. Type any one content word, and then the interface will automatically populate everything that's in the data. And so you can examine that there's nothing that has just the conscious. It's either self-conscious or subconscious or unconscious. So atomic knowledge graph is not complete. It has a lot of missing knowledge. Let's first see what sort of things are annotated. So let's select the first one. Person X is self-conscious. And we see that people annotated that, maybe person X needed to eat too much food beforehand in order to feel that way. So what does Comet do for that event that's in the training set? To our surprise, Comet does not memorize atomic as it is. It's generalizing atomic, and it's even producing new descriptions that are quite good. So for before person X needed to do something inference, so that's precondition inference. Comet generated that, the person needed to do something embarrassing, to do something wrong. Whereas people actually wrote much more concrete items. So that's quite good. And then also person X might be seen as someone awkward, anxious, vigilant. That's what people wrote. But then Comet came up with other good descriptions like nervous, shy, insecure. These are all great. And what about conscious, just conscious? So this didn't even exist in the atomic. And Comet inference is quite surprisingly good that, maybe Sarah is someone who needed to be aware, observe something, and someone who's conscious and observant, curious, sensitive. So these are all fairly reasonable inferences that Comet is able to do. And you can also give a little bit more complex sentences. Of course, it doesn't always work. But Sanya rides into the sunset on a motorcycle after solving AI. This is a little too complex. And also, Atomic doesn't have anything about solving AI. But the inference is fairly reasonable that, maybe Sanya needed to buy a motorcycle. She might be seen as someone daring, brave, adventurous. So a talk on common sense wouldn't be complete without quoting Gary Marcus. So for the fun of it, I gave this tweet, input sentence. Gary breaks the world record for the most controversial tweet. In fact, Atomic doesn't have anything about controversial tweet, but the inference again is pretty reasonable that, maybe he wanted to be famous, or he needed to do some research, write a book, and he might feel proud and celebrate, tell everyone about it afterwards. So he was quite worried about the state of deep learning, or the promise of deep learning, especially when he provides a prompt like, what happens when you start kindling and logs in a fireplace and then drop some matches, is that you typically start and then deep neural network, I think it was GPT-2 back then, would say some nonsense. So he had a big concern. But using the same GPT-2, if you convert that into Comet, so if you make it knowledge model, because GPT-2 on its own is not a knowledge model, it's a language model. So then you give Gary Staggs kindling and logs and drop some matches, you get the correct inference that, his intent is to start a fire. And so, and if you search atomic knowledge graph, again, you don't see anything quite similar to this input event. So at this point, the takeaway message is that we can draw quite a bit by combining the powerful self-supervised learning of the pre-trained language models, and they learn observed knowledge. They learn knowledge that people do speak out loud. But then there's a lot of other knowledge, atomic knowledge, that people don't usually talk about because it's too obvious. It's the implicit knowledge that people share. But I mean, we might say these things to children, on the other hand, because children ask a lot of why questions about obvious things. So almost to consider atomic is the language that we speak to these neural language model babies who don't understand a thing about the world quite well. in which case we can use language, the full scope of language as a symbols to teach the neural network with. And in doing so, we focused on causal knowledge, causes and effects, instead of encyclopedic knowledge, such as whether birds can fly or not, whether penguin can fly or not, whether penguin is a kind of a bird, and so forth. And when we use neural network, we find that it's really a powerful model for generalizing to compositional and previously unseen events. Currently, this is the only way to achieve what Comet is able to do. I cannot possibly imagine to operate directly with atomic knowledge graph just based on symbolic operations directly on top. So because we were so surprised or encouraged by this result, we also worked on Social Chemistry 101, which is knowledge graph about social and moral norms. So, but let's first think about how much GPT-3 knows about morality. So running a blender at 5 a.m. is rude because ... Well, you can wake up the entire neighborhood. You can only do it if you're making a thick smoothie and need to incorporate some ice. It's like, it's cute, it's funny, no harm made. But what if we prompt GPT-3 with, it's okay to post the fake news if it says it's in the interest of the people? Like, oh, that's not okay. How about we try again? Then it says, it's okay if it helps the certain agenda. So I crossed out the acronym because anyhow, so I don't think GPT-4 will do certainly better because, well, part of the problem is that people say all sorts of things in the internet, and there's no way AI can just figure out what's the right thing to do, what's the right, correct, ethical thing to do. And we do need to teach neural models directly with the declarative knowledge of ethical, social, moral norms. And in doing so, again, we need the full scope of language because it turns out humans are so complicated. So imagine a situation asking my boyfriend to stop being friends with his ex. Depending on whom you ask, you get all sorts of different reactions about, oh, it's not right to tell another person whom to spend time with. Or, someone else might focus more on, oh, it's okay to ask your significant other to stop doing something that you're uncomfortable with. And then if you ask my boyfriend, they might think, oh, you should make sure that your significant other doesn't feel like a lower priority than your ex. Your ex, by the way, his ex might think differently. His ex might think it's okay to stay friends with an ex. Come on. So humans are very complicated. They have all sorts of different viewpoints, depending on whether they optimize it for loyalty or care or authority and so forth. So given a situation, for any of this rule of thumb or ROT pair, we have these 12 dimensions of structured annotation, semi-structured annotation that combine categorical as well as open text annotations. And to date, we have 300,000 of such rules of thumbs grounded on 100,000 real-life situations. And part of these are inspired by this Jonathan Haidt's theory on moral foundations. So once we have a lot of data, of course, we can generate lots of tables of numbers about performances, but let's just skip over all that. And I would like to share a bit of philosophical take on this work because it's one of the frequently asked questions, like, who decide what's the right thing to do? So some people feel really uncomfortable about the fact that we just ask crowd workers, but actually there's a line of research that focus on descriptive norms as opposed to prescriptive norms. So descriptive norms can be viewed as a bottom-up approach where we just ask people what they would do, and they sometimes disagree, and it's okay. We just learn the distribution of their judgments in that case. And sometimes everybody will agree that killing somebody is not good. Although, depending on culture and religious background, maybe there are situations in which they do believe that it's okay to kill someone, who knows. But in general, for some acts, there will be high agreement, and then for some other acts, there will be low agreement. And it's really important for humans to understand even the fact that when there's a low agreement, there's a low agreement. It's a part of our common sense knowledge that there's disagreement for certain situations. So in order to get there, we need to do descriptive norms. And that's really important in order for AI to learn how to situate the judgments on a grounded particular situations. Imagine the alternative where we focus on prescriptive ethics. So we try to find the 7 magical dimensions in which everybody agrees upon. So maybe it's authority and moral, I don't know, like fairness, and you might try to find the 7 dimensions that every humans will agree on. First of all, I cannot possibly imagine that every human being will agree on one thing, though, considering all this different religious background and cultural background and their political background. Even within one country can be super divided into exactly almost half and half with entirely different belief. So I don't even know how that's possible to achieve, but hypothetically, let's just say we achieve it. Then it's almost useless for AI because AI doesn't know what to do with it unless the training is grounded on grounded descriptions. So that's the motivation of this work. Okay, so now I'll share some closing remarks quickly. If you search Commonsense from ACL Anthology, this is the repository of ACL papers. NLP papers. Most of the papers are either from a while ago or past a few years. And in fact, when I started thinking about Commonsense, I was told not to even speak the word because nobody will take me seriously. But I then realized past failures are inconclusive when they were only based on weak computing power, not much data, no crowdsourcing, and not as a strong computational models like transformers. And also, the past research really assumed that logical forms are the way to go instead of language as the conceptual representations. So I think we can try a lot of new ideas and see whether we still think it's just impossible. So path to common sense, it's a moonshot research goal. So we don't know how to get there quite yet. But I'm going to bet that it's not going to be the larger network like GPT 4, 5, 6, or 11 or 100, because you don't reach to the moon by making the tallest building in the world 1 inch taller at a time. So we probably do need to find an entirely different game plan. And in this talk, I explored some potential different paths that we might explore. And fast forward, actually, this is last year still, but to my surprise, so this was the first time we did tutorial at ACL or anywhere for that matter. And to my big surprise, people seem excited to see this. So almost a quarter of the main conference registration came to the tutorial as well. And good things happened to some of the junior folks in the team as they got tenure track faculty offers at exciting places. Some of them, Vered and Martin, are still deciding which place to go, but super exciting. So here's some questions that I sometimes get, by the way, that, oh, my dog has common sense without language, so why are you talking about common sense with language? Well, AI, it's great if we make AI for dogs as well, but I think we need to include the humans, especially adults, among the people, among the folks who benefit from it, not just dogs and cats and babies. And another commonly asked or raised issue is that, oh, you cannot really go that far with language because some concepts really require embodiment. You cannot really feel that juicy, crunchy feel you get when biting into an apple from just reading text. And so the truth is, we actually didn't really learn that tiger can eat people by experiencing it or watching someone getting eaten by tiger either. We just learned it entirely textually, and that's okay. In fact, even if, let's just say we do embodiment. we build a robot or simulation environment, one or the other. I don't think either robot or simulation environment can actually taste the apple in the way that we do anyhow. It's probably some reward function that some engineer wrote down in the code. So how is that any different from the language description of how it's supposed to feel? So I'm not against grounded research, on the other hand, in that I also do a fair amount of it, but it's just that I think I don't think any one modality will go very far. And we probably need to combine all of them and really start thinking about how we're going to connect all of these different pieces. And my speculation is that language might provide a powerful representation medium in order to connect these different bits. Okay, so almost about to end. I highly recommend this book, The Enigma of Reason, in which the main thesis is that people use reasoning in order for the purpose of communication, and human reasoning is strange. It's not that mathematical, logical thinking that we often assume as computer scientists. I think it's much more convoluted and irrational than we think, and a lot of them can be best modeled through language, or at least that's what I believe currently. Okay, thank you, and I'm open for the questions.
Ying, thanks for this great talk. So it's really a lot of things, right? So it's one idea, right, which you're extending year by year, month by month, as I can say. Especially this last part about moral norms, I guess it's also interesting. So what surprised me already back then when there were first instances of this Comet threat was that neural networks actually can extract very interesting things out of, let's say, database of, I think, 24,000 sentences, right, in atomic. So this is something which, let's say, going back maybe 10, 20 years, right, so was kind of counterintuitive to some degree, right? So let me ask a couple of questions which people asked. So Alyash asked, would it be possible to automatically extend atomic knowledge base automatically from text corpora, perhaps by reading the web in the style of Nell, right?
Yeah. So there has been such effort by different places. I think the most recent one is called OMDC. I'm probably not remembering the acronym correctly, but it's being compared in this Atomic 2020 paper. And so they have really large scale, much bigger scale than Atomic 2020 is. But because they're automatically extracted from raw text, they are worse quality. And so then the question is it better to have bigger knowledge graph of worse quality? If it's bigger, then maybe it can overcome the noise. So the paper provides close analysis about that. And it looks to us currently that the quality is important. Even, by the way, Atomic 2020 is not necessarily 100% accurate because of the fact that people do tend to disagree a little bit. When we say common sense, there's always a bit of disagreement still, but the majority of the case is agreement. And so we found that the quality does matter, but it's just some interesting question to investigate further. And in fact, I'm currently working on algorithmic discovery of atomic. So, but couldn't have the results ready for this talk. But I think maybe in a few months we'll have some exciting update about that.
Maybe if I can add to this, right? So let's say, so we were involved with psych in the past, right?
Yeah.
So we know technology pretty well. So one option could be, right, to generate sentences from psych which are correct, right? Generally, they are correct because they're created from this handmade knowledge base, right? So this could be one way also to generate correct sentences with, well, only as a tool, right? And this could be not language model, but knowledge model, right? So going
Absolutely. Yeah, in fact, this paper, we wanted to do head-to-head comparison against the research psych. So we were begging them to share that with us, but they stopped the research psych license. So in the end, and they do have an open psych, but I don't think it has all the juicy part to the research psych or their the full psych does. We didn't do that because OpenPsych seemed like way too taxonomical. It's just yeah.
No. Juice was drank by duck in OpenPsych. So if I may say a joke, right? Let me check another question. Common sense is the most fairly distributed thing in the world. For each one thinks he's so well endowed with it. Aha, this is just the quote, right? Pierre, maybe if you would maybe put some kind of question on top of this would be interesting. Or maybe if you can comment this sentence. I guess we can only agree with this, right? Yeah. So one very obvious question or comment, right, is on okay, the way how you approach the problem is okay, you have the data, you have some labels, crowdsourced and so on, right? But common sense, as you pointed out at the beginning, right, deals with these uncountable concepts, right, which not where only some come to the level of the words, or they get the privilege, so that a word, literal, right, is designated to it, right? And now, let's say, even if we look at the knowledge base like psych, which tries to be this common sense knowledge base, right? So it has this, in principle, it can derive uncountable sentences or claims or facts, right, about the world. So my question is, let's say, I'm sure you were thinking about this, how to constrain certain inferences out of the model with some maybe simple rules, right? Simple rules or ontological old-fashioned approaches, which, well, maybe some of the people wouldn't even allow you to name, right? I remember last year at AI, Dan Roth was apologizing at 2 or 3 occasions using the word logic, right? So he said, well, I apologize. So I dare to use the word logic, right? So the question is, would some simple constraints, right, in the form of rules would help resolving some of the issues, right, here and there?
Yeah, absolutely. That's a great question. And in fact, I also dared to use logic, although right next to neural. So that doesn't sound like I mean, so we do have the thing is, so in this work though, the logic constraints are only an input. I guess the discrete search itself does have old-fashioned computer science flavor to this. So if you look at the details of the algorithm, there's nothing modern about this. This is search algorithm that used to be one of the main focus of the AI. At least it's the beginning chapters of AI textbooks. So it used to be very important to deal, especially this logic satisfaction, constraint satisfaction was one of the important part of the research. So we are bringing that into neural network and trying to emphasize the importance of algorithm a little bit more. But this one does have a limited scope because we only worked with lexical constraints so far. And of course, we want to be able to think about other kinds of logical thinking, such as negating a sentence or so we actually have a different recent work about atomic that focus on negated sentences because Comet is weak. If you try to break Comet, try negated sentences, it may or may not always work. And that's copying the weakness of a neural network in general. Neural network themselves are, the neural language models themselves are not very robust against the negated sentences. So we have a new version of Atomic called Anion. It's just a cute name that focuses on these negative aspects of atoms. And in it, we explored a little bit more into that. But it's a research direction that I think requires a lot more investigation to find a better way of incorporating logic-like constraints. I wouldn't dare say that we are anywhere close to having a satisfactory solution.
Just one last question from Daniel Schwabe. So how do you envisage explicitly integrating human values in the moral norms, where moral norms embed points of view of people, right? So I guess you might have some answer about this.
Yeah, so basically this social chemistry does try to achieve that by asking, but we try to do this very larger scale because otherwise we may not, this was a bit of exploratory work to see how complex this can be, and the annotation process was incredibly hard and enlightening at the same time in understanding how complex the moral system is. It's very easy to assume that, there must be some simple dimensions, basic dimensions. But if you actually look at various examples, then there are always weird counterexamples in which the original ontology or original annotation scheme doesn't work anymore. And we found that it's very, very messy. And yet somehow humans learned it. And so one way to mimic that might be the way how humans learned, which is all through just natural language description and natural language interactions with other people. That's how humans acquired value system. And so this is how we are trying to explore that.
Yeah, I remember your talk when you were presenting the experiment itself, right? So you picked, if I remember, wedding or marriage or something like this, and how Indians and who were the others, Americans or somebody else, look at the values around some of these very fundamental concepts of societal norms, right? They were quite different, right? So this was very interesting. Anyway, so we are getting late, so I guess ESTEVAM is already nervous. Ying, so really big thanks for this great talk. It's so much content, and I think this topic will has a long way still for all of us, I guess. And I guess we'll meet more around these discussions. Thanks again.
Thank you.
And now we are switching to the second keynote of the evening, and this is by my very good friend ESTEVAM HRUSCHKA. So as I said at the beginning, so the point was somehow to complement Ying's talk with which is more like on the exploratory academic side, right? So while ESTEVAM is still with one lack in research, but still tries to solve some of these real-time real life problems, and make some of the services happy as well with similar technologies, right? And maybe just a few words about ESTEVAM. So ESTEVAM is now research scientist in Megagon labs. And before he was co-leader of NEL system, never-ending language learning at Carnegie Mellon. So this is where we met years ago, and this was one of this, let's say, I would say one of the after psych, one of the first trials going in the direction of common sense reasoning with some significant results, right? So before coming to US, ESTEVAM was in I phone is ringing. In Federal University of São Carlos in Brazil. And he was fellow of Brazilian National Research Agency, Young Research Fellow at São Paulo State Research Agency. He also received the Google Research Award for Latin America, and he was visiting professor at Carnegie Mellon. This is where he was doing the work on NEL. So his research interests are broad in AI, but mostly in this very challenging area of, let's say, deep understanding of text. For just before joining Megagon Labs, he spent a few years in Amazon in Alexa search team, so he has also a little bit of experience also in this area, and I think he contributed to Amazon mobile app, which I guess everybody's using, to the chatbot, if I remember right. And so this is as much as I know, right? I mean, there's so much more to say. But Estevam, please start.
Marco, thank you so very much, and I would like to also thank all the committee, and congratulate you guys for putting this conference up. It's so nice to see community together, and we do know how much work that represents to the organizers. So we deeply thank you in the name of the community for sharing your time, giving your time to our community. Thank you. It's a great pleasure to be here. I will start sharing my screen so that we see. Do you see my screen?
Yes, we do. But we see we don't see the.
Yeah, I'm trying. So let's move this and go for just a second. And I'm sorry about that. But getting there. It's just the other window that was there. Good.
The last talk of the day has privileges,
So yes, so this is the presentation. So do you see the presentation?
Yes.
Thank you so very much, Marco. I don't see you guys, so if you need anything, call my attention by audio, please. Okay. But today we are here to talk about implications and explanations from user-generated data. As Marco mentioned in the beginning of his very kind introduction, is that we are going to try to also take a look into knowledge-based construction or knowledge stored in some form that can be useful for machine learning, AI applications. But I will try to complement some of the possible work that we can do, focusing a little bit more on user-generated data. And the main reason for that is that YEJIN already showed us great work that has been done. I will try to call attention for some different dimensions that we can also explore. This work is actually not a work I've been doing by myself, so I will go from some previous work and old-fashioned AI and things like that, and then to more recent works that are exploring this line of reasoning for common sense and knowledge base and so on. But this is actually a great effort from the whole team that we have at Megagon Lab. So I thank my whole team for this. This is a joint work with them all. Okay, so let's start just defining a little bit better what am I talking about here when I mention user-generated content. So this is the thing that nowadays is very frequently available over the web. And we are here at the web conference, and everybody that has access to this kind of resource nowadays really takes advantage of, before doing anything, checking online, checking the web. Imagine if we now got to know about Ljubljana and we want to go and visit that great city that we have over there. I might, before doing my trip, whenever it starts to become safe again, I hope soon, I'll go over the web and say, okay, what hotel should I stay there when I'm visiting Ljubljana? Yeah, what are the must-see attractions there? What should I buy when I'm there, and so on and so forth. There are so many things that you can really take advantage of the web to help you on take decisions. And for instance, I can go over hotels websites and use that to read the reviews, and you're going to see that we have a lot of reviews about many different hotels over there. I can notice that they might differ in the opinions, so I would read a bunch of those, then build my own conclusion and take my decision. Oh, this hotel is good enough. Or sometimes I need to read all of those reviews, but then because there are so many and things like that, I'm not really, or because I didn't find what I was looking for in those reviews by reading them, there are so many and so on, I sometimes can go for question answering or questions and answers that are available by the community, and then taking that I can read answers for my question. What would I would like to know, for instance, how to get there from the airport and things like that. The hotel, in this case, answered this question. There are other people also answering, so on and so forth. So you see that we can really explore this domain, and there is a bunch of information in this form of user-generated content that can help us. If I now say, okay, I got my hotel, I want to check what am I going to visit, and then I just do a search, and I'll find a bunch of options here. And then after having those options, I might go, okay, I need to get a little bit more detail about the castle in Ljubljana, which is a great place to visit. And you see, we have here, for instance, this comes from Google, some description given by Wikipedia, as you can see. But you also have a bunch of user-generated content here. Wikipedia is kind of user-generated too, but let me take that as a little bit different. And we also have, for instance, reviews here, more than 24,000 reviews with many different ideas or opinions or subjective thinking about that attraction and so on and so forth. I might want to read some more and so on and so forth. So that's what I would do before visiting, mainly if I don't have friends there that can tell me more. Yeah, but and then I can say, okay, now I visit the castle, I am in my hotel, but before going home, I'd like to buy something so that I can remember about Ljubljana. There are so many things that Ljubljana is great and you could buy. But one of the interesting things here is that the honey there is really great, and they have this honey bee stuff. So honey, actually the beehive things that they draw upon it and make this nice kind of pictures and so on. So I might want to buy one of these. So then I would go to some web site and find some reviews about that and so on and so forth. So you see that I can use it a lot, and I can benefit from having this user-generated content as a user, as a human being. But as I mentioned, the number or the volume of information that we will find out there is too much for me actually to go through all and so on and so forth. So here we get actually a number of different interesting relevant tasks that we can apply when we are working with AI, machine learning, and this kind of topics. I just listed a few here. So, and remember that in these examples I was mentioning to you, I just talked about reviews and questions, questions and answers. So we can do review retrieval or summarization or finding contrastive reviews, salient facts inside reviews. For questions, we can actually try to answer questions based on the reviews. We can deduplicate them, answer, find summaries for the many answers, so on and so forth. So many. And you can even go for other domains. We don't only have user-generated content for reviews and question and answers, even though I will focus more on this here for this talk. Okay, so this is actually an opportunity for us, because the users want to use this data to go beyond what is the official view of the hotel or things like that. They want to experience or learn from the experience from other people that did already that same activity that I am trying to do, okay? But it's too much because we have too many examples and reviews and so on. So we see here great opportunity. We should explore more and try to apply this kind of, use this kind of data to build models that can help people in these daily lives tasks that they have. Actually, there are many people already working with this and applying different models and proposing different ideas. But it's important here to mention that we have some very specific characteristics here that usually make traditional models not so suitable for applying or straight just go and apply what we have, some off-the-shelf models and things like that. Some of those characteristics are, this data is really rich on subjective and opinionated facts. It means we are not talking about things usually that we find in Wikipedia. We want to go beyond. I just showed one example that if I'm looking for the castle, Ljubljana Castle, I will find the description in Wikipedia, but you know, I want to go beyond that, and I want to go and know the feeling of the people about that attraction and so on. So this is different kind of data, and this is usually when it becomes a little bit harder to just extract knowledge, build knowledge bases, build common sense knowledge bases or language models on top of it, because they have very specific characteristics. The relations are not very explicitly stated here. And so we really, when you are reading a review or many of those user-generated content, you need to read between the lines. It's not actually that the person will express everything in the sentences. There are lots of things that you need background knowledge, you need common sense to try to understand. Yeah. So here are some very few examples that we extracted using sample, one of the work that we that I will present here, and we are doing, and we are working at Megagon Labs. So in the hotels, if someone say, okay, the room had really thin walls, you know, it's very easy for us to understand that if I stay there, that might be noisy because of the thin walls. Yeah. In the movies, if someone said, okay, that was an original plot, and then I know, okay, this might be a very unique movie, and so on and so forth. For pet supplies, good food might be inferred, or real meat might be inferred. Good food might be inferred by having real meat. In electronics and so on and so forth. Yeah. So this kind of implications, and also some kind of explanation from what we are reading and why we would have some conclusions about what we just read. Those are very important. And in this case, common sense, background knowledge can help us a lot. So let's take a look from this point of view, that it should be very useful using common sense and background knowledge approaches for solving the problem of understanding user-generated content. And being very brief here, because YEJIN already did a very nice explanation about some of the work that are really, really key in this area. So thank you for that. Also, there are some very interesting tutorials around this topic, as we were just discussing after YEJIN keynote. The topic is really coming back to be very actively researched and so on and so forth. So I would recommend this ACL tutorial, in which YEJIN is there, and this other triple AI tutorial this year is also very nice. And in all those approaches and the keynote and so on, you're going to find that we have very interesting models, but in general, what we see there is that we have a focus on more factual knowledge and these kind of things. So the opinionated knowledge, the more subjective knowledge, this kind of the feeling of the user, it's not really the focus of most of those works. So this is one thing we should consider, that depending where you want to apply, you might need to have a little bit different approach because of the kind of data you are working with, okay? Also, another very interesting thing that we might want to consider is that whenever we are building some knowledge or we want to extract common sense knowledge, we might want to go beyond only the triples that you can see in your knowledge base or something like that. This is something very interesting, for instance, when you use your your language model as a knowledge base, or kind of this kind of thing. So YEJIN was just presenting some ideas on that. This is good because you actually don't use only triples and match them to solve the problems you want to solve based on the common sense knowledge. But it's also a little bit different from, for instance, what was done in now, the never-ending language learner that Marco just mentioned, in which we were also trying to explicitly have in the knowledge base or in the knowledge that we were accumulating, not only the triples, but what was behind the reasoning or the learning process that happened for that triple to be generated. So let's look a little bit more about these characteristics whenever you are trying to learn or extract common sense knowledge, but you also want to keep track of it, and so on and so forth. Okay, just very brief introduction here. I don't want to spend so much time here, but now is this system that was reading the web in this project called Read the Web project. Let me call you your attention to two things here. The project was actually designed to try to solve two main tasks. Okay, the first one was, as it's written here, attempting to read the web, so web documents, and then extract facts from it. So this is much more kind of building different models that can help in the information extraction part of it. And when we are doing this, we are trying to build the triples. So I know that George Harrison plays the instrument guitar. So you see the triples are here. And part of what Nell was trying to solve, yes, was fulfilling or populating this ontology. Surely it was also extending, trying to extend in some sense. But the population here was really, really strong part of what was being done there, okay? And in this sense, here are some examples. Nell was learning that the White House conference is a conference, for instance, and then keeping some confidence here on the facts that were learned. Lewis is a person who graduated from State University. You see, some of those are very general. Some of those are more fine-grained, and some of those might be wrong, like dog shampoo is a personal care product for dogs, yeah, not for us actually, so not personal, and so on and so forth, okay? This is what I mentioned, the task for building the knowledge graph, let's say, or the triples that will populate the graph, as we were saying. On the other hand, Nell was also focused and strongly focused on a second task, which was where it was attempting to improve its reading competence. So actually, to be a little bit more specific, in the first task that Nell was solving, it was just using the models that were already learned to extract knowledge from the web and populate the knowledge base. But on the fly, so while doing this, Nell was also running in parallel a different task, which was, okay, how can I read again, let's say, the same set of documents, and now being able to extract even more, or being able to extract with more precision, or things like that. If I need to do that, I need actually to improve my own competence on reading, actually, not only just populating with a static model that was there. Yeah. So in this sense, look, now was created based on an initial architecture, and this architecture was actually giving to Now the ability to build its own internal representation. So we nowadays talk a lot about the internal representation that we have with this dense vector representation from neural language models, which are great, yeah. And what we have in there is something that you pre-train, for instance, so you accumulate some stuff, and then you can use that to solve your task. But you can come now and fine-tune it on a specific task and then improve or refresh, let's say, your dense representation vectors, and now you apply again in that different subtask and so on. So now we propose some mechanism that was going towards this, but in a different way. And I would say that I will mention this in a few slides, that we really cannot get the speed and the let's see, the broad scope that a language model can get with these dense representations that they have. But let me just give you some context. In now, we were trying to do something similar to that, but specifically focusing on, if you have in your architecture one component that would be based on extracting knowledge based on contextual patterns, let's say the mayor of X is a contextual pattern to tell me that X is a city, or if you are, and if you also have another element here or component in your architecture that works with orthographic classifier, then if I read Pittsburgh because it finished in Berg, I will learn that this has evidence to be a city, and so on and so forth. And if I have, for instance, images there and I see the pattern of two images and say, okay, because they are similar, they might be from the same concept and things like that. So this is what actually this architecture was what Nell was using to generate its internal representation for facts and the concepts and the relations that were there. So giving an example for this contextual component that I just mentioned, Nell was learning things that an athlete, would have this, for the relation that an athlete plays a sport, we would have this kind of textual patterns. For instance, ARG1 being the name of the athlete. So let's say Michael Phelps is the Tiger Woods of swimming. So ARG2 is the sport here in this case. And you see that whenever we learned this triple, that Michael Phelps is the Tiger Woods of swimming, this goes to our knowledge graph, so the graph that I told you we are trying to populate. But now keeps provenance or keeps its own internal representation, which is not a dense one like in language models. It's actually a sparse one and more symbolic, which makes it harder to work with, But on the other hand, brings us this ability to double check and know what is going on, and what Nell learned that allowed it to now understand that Michael Phelps is actually an athlete that practices swimming, something like that, And it also gives us, so as I told you, depending on the architecture we put there, that's what will be forming our internal representation. If I have this seal, which is if I have this morphological classifier that I mentioned, and I will learn things like that. Okay, if a noun phrase has as the last word in this noun phrase university, so there is evidence that it might be university. So Carnegie Mellon University, things like that. You see, so that was actually in all the sparse vector representation that Nell was building to represent everything that is there. It would even give us the ability to come here and detect, okay, in this case we have, let's say, swimming, architect Robert Trent Jones, and argument 1, which would be, I don't know, name of an athlete, John, I don't know. You see that this is something that Nell learned as a pattern that should be useful to learn more pairs of noun phrases, one being an athlete and the other one being a sport. But you see that this guy here is very specific to this Robert Trent Jones. And you see, maybe this is not a good one. So what I mean is that whenever you have a sparse representation of what you're learning, actually, or of what your models use to learn, you now can even come back here, double check and delete or understand some biases that your model has and things like that. Anyway, you got the idea. This is what we have. Now, as I mentioned in the beginning, I also have some part of this learning embedding. So it also had in this big, huge vector representation, part of it was kind of dense, and then you can just check things as we do with language models. So I'll go a little bit faster here because I'm taking too long. And then that could be used to explain, and now for sure was also using these reasoning ideas as many or almost all knowledge bases that use some kind of reasoning on top of their graph representation or something like that. So now was using, and that could create for us some also rules that could be interpretable and things like that. Okay, so in this case, we could use for inference and implications. And we could learn things in many different ways, some probabilistic random walks, as I was showing here, or we can go for more logic-based approaches, in this case, some probabilistic horn clauses, and so on and so forth. Okay, but for now, learning and improving, this internal representation, this vector representation, sparse vector representation of the language was the most important thing for the system, so that it could be a never-ending learning. Because then when I learn a new set of examples and I populate my knowledge base, I could come back and refresh my vector representation with these new concepts that were just learned. And so in the next iteration, I could do it better. In some sense, there is some overlapping here, as I mentioned before, with this idea of never stop pre-training, or even the fine-tuning approach that we have. You have a pre-trained model and you fine-tune, or you transfer, you adapt, and all of these things that we do with language models, but when we use the language models, as I mentioned before, the internal representation is not so easily verifiable, let's say, or we cannot take the explanation so easily from that part of it. So we need to explain it using different approaches, And now it's easier to work with that kind of explanation. But on the other hand, if you want to build a system like now, the architecture is very important part of it. And depending on the architecture that you put in your never-ending learning system, that will reflect in the internal representation that you are building. And this can be really harder, and it can take much, much more time to build something like that than using a language model as we have right now. So it's not easy to say, oh, this is better than the other one, or vice versa. Like all of those approaches, they have pros and cons, and we should pay attention on what are we trying right now. And so based on that, we can build some models that might benefit from specific characteristics that we have and that we have learned with the previous works that are already there. Okay, as I mentioned, so we have all of these. We can learn from these experiences and so on. But we don't have much on this when we are talking about the subjective knowledge that we want to extract, okay? So instead of just building upon those approaches that I mentioned, we start to look at this problem a little bit different and putting, instead of extracting named entities, for instance, or concepts and relations between them and so on, we decided to start looking at some user-generated content, getting opinions as the key element or the basic element of it. So can we, for instance, create an internal representation for reviews, let's say, that are based on opinions, and that can bring us extra knowledge that would not be easily extracted using the traditional model. So this is something interesting here that we want to discuss from now and on in this talk, okay? So based on that, aspect-based sentiment analysis is not a new task. Like it's relatively new, but not that new. We have a bunch of nice and interesting works out there that do this. And the description of it would be, okay, imagine you have here a review, and the review would say, would definitely return as we have no complaints. Elevator was a bit slow, breakfast was not very exciting, room was small, but this isn't a 5-star hotel, and it was perfect for our needs, so on and so forth. Okay, so the aspect-based sentiment analysis task or idea is you go here, you identify some aspects of this review, and then you identify the opinions that are related to that aspect. So, for instance, for the aspect elevator, the opinion here was a bit slow, and the sentiment would be negative maybe. And for breakfast, another possible aspect, not very exciting, so on and so forth. So you got the idea, yeah. So using this kind of approach, we decided to go and build a first pass over some reviews or some user-generated data and identify aspects and opinions in those so that we can start building something from it. Instead of just using off-the-shelf tools for that, we have some very interesting ones and good ones actually, but usually they need lots of labeled data. So Megagon Labs teams worked on trying to build snippets, which is this work or paper that was presented here in the web conference last year, yeah. And in that work, what our team did is like we just tried to generate aspects and opinions or extract aspects and opinions from text without needing so much labeled data. So we applied some techniques related to data augmentation, yeah, and then we added the ability for the model to work with labeled and unlabeled data. So in general, what we did, we based our work in language models, yeah, but we provided as input labeled data and augmented data that is artificially labeled, plus plus unlabeled data here. So that's the main idea that we have. Using this, we could really label or extract aspects and opinions using much less labeled data, which is very good. We beat state of the art. So you guys can see more details of this in the paper. We extract them. We did some experiments in a bunch of different corpora. Some of those here for hotel reviews. We can have this kind of idea. Definitely recommended. This is the opinion, and the hotel is the aspect of it, and construction is the aspect. Going on is the opinion. And so on and so forth. So this is what we were extracting. We have a demo for this, so if you want, you can just grab your reviews and post it here. It will extract the aspects, opinions for you, and so on and so forth. But the goal of this talk is now to show how did we started from that. So now, okay, we have snippets. We can also use other tools for extracting aspects and opinions. And okay, how that could be now useful for us to create a representation of the user-generated content or data. Yeah. So the idea is the following: we have the data, we apply aspect sentiment analysis, and then based on that, you have what I just mentioned to you: bad service, great location, and this kind of things. But you know that just doing this, we don't have actually the relationships between or among different opinions. Yeah. In addition to that, when we extract this kind of things, usually you get too many duplicated opinions and things that are exactly the same, but your model didn't know. So it's still very hard to use this kind of thing as they are, and only the aspect opinion extraction results to represent your text and things like that. That would be actually too noisy if you use it for any other downstream task from that data. So what we have been working then is on the following. Some other work has been done, but I want to show you here two interesting next steps after you having the reviews and having extracted the aspects and opinions using snippets, for instance. we are also exploring it in two different ways. The first one is using sample. The paper from our team was published last year, AKBC. You guys can check it there. And also trying to get an explanation based on the entity itself, which is explain it, another paper from our team that is going to be presented here at the web conference tomorrow. So please be our guest to attend and get more details on that. I will actually briefly explain and give an overview of both of them. Okay, let's start with sample. The idea of having those two ways of representing the user-generated data is the following. The first one, sample, that I'm going to show right now, is more like a global representation of it. For some of you that were familiar with now, Marco, I know, knows about that. We were doing here what we used to call at that time a macro reading. So we get a bunch of reviews, let's say, and we want to extract characteristics that are common or are frequently stated in this general overview. You know, so we are not focusing in one specific hotel or in one specific product or things like that. We want to extract the general common sense that could be used in that kind of domain. So it's domain specifically, usually we did, but not entity specific. And in the second one that I will show later, we are more entity specific, and I will talk more about that in a few minutes. So sample is the first one. This, as I mentioned, is a work from last year, AKBC. And the idea is that, okay, we want to actually extract or learn, and this is an unsupervised way of having extracted aspects and opinions. How can we identify implications on those? So the idea is that an opinion is a modifier and an aspect. In this sense, I would say that, for instance, we have fast-paced action would be an opinion. So it means for the aspect action, the modifier is fast-paced. And let's take this from the review. For instance, the movie has everything: fast-paced action, romance, and complex characters. So that's it. So complex characters would be another one, and so on and so forth. So that's what we are talking about here. We want, from the aspects and opinions, build a way now to detect implications. So let's see, can we learn that whenever we find a complex character, or that the movie has complex characters, would that imply that this is really good writing? And this is kind of things we are trying to learn when you represent your reviews, in this case, using aspects and opinions, okay? We can then use this in many different applications, as was done there. Let me go very briefly over what we were doing here. As I mentioned, this is a non-supervised approach in which, when you start from reviews, you can extract aspects and opinions using snippets, for instance, or any other one. Then we build this matrix here for every movie. In this case, we're gonna have the aspects and opinions, or and modifiers here that we have creating the opinions for those movies. And then we do some matrix factorization, and now we can generate a representation for those movies and things like that. And we can try to extract implications using some inference based on the k nearest neighbor approach. Very simple one based on the matrix representation we are having here. So that's how we are extracting that complex characters might imply in good writing and this kind of things. So that's the approach. This approach is unsupervised and brought us very nice results when applied, for instance, to this knowledge-based completion or completion tasks. Okay, so we compared with some of those, did kind of well when compared to those basic approaches, and some and even comparing to just the basic language model. At that time, we were just using BERT. Performance tends to be good, and you see that the more, depending on how much training data you can get, yeah, you can actually improve your model. So you can use your knowledge base to generate data, and then use that data from your implications or opinions implication knowledge base to reinforce or refresh, as I was telling in the beginning of the talk, your internal representation of your BERT or language model, and then based on that, you can get better results. That was we showed here. Some examples of what we automatically extracted in this unsupervised way was like for movies, we had like satisfying ending can imply in good script. Believable acting can imply in interesting movie, so on and so forth. For cooking or restaurant, so great meal can imply in good restaurant. Delicious menu can imply in tasty dishes, so on and so forth. For fresh fish can imply good sushi and things like that. For electronics, responsive key can imply nice keyboard, so on and so forth. For books, yeah, you can also have some interesting twist, unpredictable story, and interesting facts that we can have from the implications. So summarizing here, one very interesting result that we got from this sample work is that depending on the domain, we always get from 15 to 25% of the implications that, for instance, BERT could not understand, or it was not already in the language model or in the knowledge that the language model pre-trained using BERT and adapter or fine-tune to this task would have. So we can pre-train, fine-tune, but these are kind of implications that we don't really find just doing this. So this is interesting result. It shows that we can actually enhance the model with this extra information. Something similar to what YEJIN was just showing. Yeah, if you have a knowledge base, you can now use this to work with a language model and put them together in a way that your language model can now incorporate some of this kind of knowledge. We did this using, in this project at Megagon that we call Access, actually incorporating or injecting it inside the language model itself. In this case, we tried concatenating it and so on and so forth. Yeah, and this helped us in aspect extraction, in aspect sentiment classification, and it also brought very good results on question answering downstream tasks. We also use this kind of knowledge base to improve actually the ability that we have for creating, let's say, this kind of benchmarks or creating data sets that could be more could be harder actually to be solved, and then helping the community to try to advance in this area. So we did that, and we applied it, and we have this paper last year in EMNLP in which we provided. So we released this knowledge, this question answering benchmark based on this. We can also do data augmentation as already mentioned, and I'll just let you guys know that we have this available with this demo. Yeah, so feel free to go and use it. You can, in the demo, actually, we just provide, in this case, some specific initial data sets to work with, but you can go run on this and extract things. Let me try to run for the last part of our talk. My time is running fast. And then I told you that we want to explore how can we use aspects and opinions to construct or to build a knowledge, an internal representation for use-generated data. And I want to use that to apply in different downstream tasks that can be helpful for us. So we want to build this knowledge base, or we want to extract this kind of knowledge that is common sense from reviews based on the opinions, instead of just going for the facts or using the facts that are in this user-generated data. The first one that I showed you, which is sample, and we have it available, even the data set we generated and also the knowledge base. It was very focused on the macro reading idea. So we were reading the user-generated data and finding, extracting implications that are general for that domain. Now, what if we want actually also help our user to better understand specific entities? Yeah, so not only extracting the general knowledge that we might have on that domain, but specific things about your specific entity. And as I mentioned, this is an Explain It project we have at Megagon Labs, and we have a paper on this describing exactly how we do this that will be presented tomorrow. And this is the paper. Please feel free to attend. I recommend. But here's just a very initial flavor of it with not much spoilers here, okay? So what we do that in that paper is we build actually an opinion graph. That's what we do. So based on the reviews, we also use aspects and opinions, and then we build a knowledge base, let's say, that is an opinion graph in which we put relations between opinions, and those relations can then help us actually to better understand the different opinions we might have for one specific entity. So you see that we have some key features here. It's very easy to interpret when you use this kind of things. It's concise because now we don't have that problem of having duplications and repetitions of opinion that mean the same thing, but the user doesn't know. It's very easy to explain when you look at this, and it is entity specific. So those are the main characteristics that we have. You're going to see tomorrow in the presentation that we did some human evaluation over this, and people really see that these clusters that we find are very relevant. We had already at the web conference last year a demo that was showing this thing, and we also have the demo up and running for you guys that want to try with the models that we're going to be presented tomorrow. So just to give you a very, very quick flavor on this, I don't want to spend too much time on this, but let's imagine you are the user that I described in the beginning of this talk that is wanting to understand what are the hotels that I should consider when I'm going to somewhere. Yeah. So then for this hotel, for instance, what will happen that I will not have time to read 3,000 reviews. So in this Explain It project, we actually use the idea of from the reviews, extracting aspects and opinions. And then from the opinions that we can have there, we learn automatically. We have a sequence or a pipeline to learn the relations that happen between those opinions. And then based on that kind of relations, we can explain, for instance, the way we see that specific hotel based on the reviews that are given there. So that's the main idea here. Let me just show you that I already mentioned it's a bunch of reviews. I will not read them all. So what our Explain It model proposed to us is to have the strong, let's say, aspects and opinions that we found on the reviews, and they will be shown here in this part that I was showing. Yeah. So in this case, for this hotel, aspects and opinions are like friendly stuff, nice hotel, lot of homeless people, and clean room. Yeah. And then you see that we also generate, based on this aspect opinion representation, a summary of all the relations that we have. And in this case, it would be like, sorry, not all the relations, all the reviews, summary of the reviews, which would be, and this is an old hotel with a lot of character. The beds were comfy, so on and so forth. The beds and sheets were always comfy. Front desk, a lady was friendly, and so on and so forth. Yeah. And then here in your right side, you can read the reviews based on any of these opinions we found here. So I just click in one of those, and then I will find reviews related to that. And we have the graph here showing us actually how much these things are explainable by the other. So for instance, the hotel is in a bad street. We extracted it from the reviews, and that causes that this is not a very good neighborhood, so not the greatest area, as you see here. And because it's not the greatest area, there are a lot of homeless in that area. Okay, another one is like many people might have referenced this older lady that is in the front desk, and she might be very friendly, and then you see it can be explained how this lady actually generates this feeling or opinion that this is a hotel with friendly staff, and also helpful front desk contributed to that. And so you see, you have this explanation or idea of relations among the between the opinions that we have. Let me just keep going. I can, as I told you guys, click on specific opinions and get the reviews for them. So friendly staff, homeless, lots of homeless. I can also come here and say, okay, I don't want to pay attention on this opinion. I can come and delete it. And if I do it, so then you see that the graph is updated, and I'm focusing more on those three. And you see that even my textual summary is updated now, focusing more strongly on those three ones and so on. So that's how we are using the idea of constructing the graph from the reviews or user-generated text or content. And yeah, this is kind of the summary of the idea I want to show you. I would like just to go back now and say what we discussed today was just very briefly review on some aspects of most of the models we have extracting common sense knowledge and representing it in different ways. Actually, I didn't went through much of that. YEJIN did that greatly before myself. I just mentioned that most of those models or techniques or approaches are focused mainly on factual things. Whenever it's more opinionated or subjective concepts, we don't have so much work being done right now. And also in most of those approaches, we don't have a very easy way to go for the explainability and implication and things like that. I called attention that in now we were trying to, and now actually makes it explicit, what is actually the symbolic internal sparse vector representation of everything that is learned, but then it makes difficult also to go and apply so easily. You need to build a system with a specific architecture and so on. We, based on all of this, started building a way to represent or to create internal representation for user-generated data that is based on opinions, and then how those opinions relate to each other, and how can we use that to solve some tasks for the users. We have some references later here from what I just mentioned. And so with this, I am going to thank Marco, the whole the web conference committee. Once again, say thank you for putting your effort and time, precious time, in pro of our community. I really appreciate that. I think this is an important thing to be mentioned.
Estevam, thanks. This was a great talk. I think we learned a lot. So how things are actually done nowadays, dealing with the reviews. Let me start with a quick question, right, by Elias. So the question is, so this knowledge graph which you are building, right? So this is, showing this to companies, right? Everybody would say, well, I want this, right? So it's something which it's a kind of a summary which is useful, right? So this is something which we could say about this. So the question Elias put is, do you have also in the graph opposite relations, right? So if you have on one side cramped space means also opposite from spacious bedroom, for instance. So would you operate a little bit on this?
Yeah.
You're muted.
My goodness.
Yeah, now it's fine.
Yeah, okay. So thank you, Elias. Thank you, Marco. Great question. So in the sample knowledge base that we are building, the implications are not actually constrained or restricted. So we can have this kind of things, like one information or opinion implies on a negation of the other one. So, but usually this will happen in the model that we have right now only when the negation appears as an opinion too. So we are kind of constrained on that. That's what would limit it. I would say that I can even go for and try to remember about the negation or negational implication that we found. I will not remember from top of my head. So I would say the following: it depends a lot because it's unsupervised, and we just try. If I can give just a brief idea of that, I told you it is kind of matrix factorization, yeah. And so we get the opinions for movies and so on, and then we actually try to do kind of. It's not exactly this. We can go for the paper for more detail, but the intuition would be similar in some sense to doing frequent item association rules that you guys know a lot how it works. Yeah. So if we find frequently some items or opinions in that thing, and then we notice that in the other movies we don't find the inverse or things like that, that's how we try to build this implication in that model based on the matrix factorization that we built. So it means that if one of those opinions is actually a negation, so not spatial, I will just make it this up, not spatial, a spatial's room, and we notice that a previous opinion or an opinion that is also very frequent for that thing appears, and kind of whenever this appears too, so we will actually extract that. So that's the basic and simple approach that we use there. So I would say there's no limitation in get there, but in extracting that whenever the negated opinion appears there. So it's totally all based on the opinions, but now let's go for the limitation. So it brings us on the same page as we discussed before in the previous talk. When the atom here, our opinion is our atom here, a little bit different from a concept or an entity as we were discussing with YEJIN. When the atom here is not negated, adding a negation on top of that is still something we don't solve because we are not really capable of understanding the negation previous to this opinion yet. So when it's captured and becoming the atom, yes. Whenever it's not, that will not be captured. I'm not sure whether I could answer it very well. But
I think you did actually. So one maybe related question. Now you showed this creation of these graphs on, let's say, hotel reviews, which is fine and useful, and many services, I'm sure they're happy about this. But let's say, what if you would imagine now election campaign, right? Lots of articles with lots of opinions and forums writing weird stuff, right? And too much of it to read, right? So could you summarize, for instance, something like this, like forums, tweets, something which is impossible to check manually, right?
So that's an awesome question, Marco, because look at that. The works that I just presented here is the part of works that we are doing at the lab, focusing explicitly on the opinions. So before just answer your question, let me tell you that there is nothing that prevents, and actually we have some approaches that we are working in which you can have aspect and fact, and then aspect and opinion. So actually, for what I showed here, we are just using the part of the knowledge that we consider as being opinionated and subjective, but we can also put it together. And where I'm trying to get here is the following. Whenever you have an article from press, let's say, or news, so in that kind of content, usually you also have more facts, yeah? Because the person usually wants to introduce you the topic, explain a little bit on that, and then drawing opinions and discussing things like that. So you see that whenever that happens, that you have more factual information together also in the text, if you apply only the opinion part of it to represent that element, and let's say in that case it's an article instead of being a review, So what we are doing here is building the elements that we want to use to represent that passage of text. Yeah, in the ones I showed to you, we are using only opinions. We can do it, but what I would say is that if we use only opinions for a text like an article, it probably might miss part of the factual information that is there in the article too, and that could be useful for the internal representation. So what I would say is that these approaches we are working, they are suitable for this, but in that case, I would not filter out only the opinionated part of this representation, and I would put together facts and opinions in the same representation, and then trying to work with them. This is kind of what we did in the work sample that I showed, in which we get the implications that are from opinion and then trained or embedded those in a language model. So the language model has a lot of knowledge about the facts, yeah, or factual things that it was learned, that they were learned during pre-training and so on. So when you embed this kind of thing, now you kind of put together the factual part with the opinionated part, and then that's how I see it would work well. And if you're not working with a language model, you want to apply straightly your knowledge base or graph, then I would say it's worth putting your graph as a hybrid version of this, in which you have the facts plus the opinionated or subjective knowledge. That would maybe bring even more benefits than working only with the opinions. But in summary, yes, it applies, it works. We are actually trying to build this kind of internal representation for any model that would try to extract knowledge from passages of text in general.
Yeah, great. No. Just YEJIN said that she really likes the demo and the your approach, right? Maybe you can read it on the left side, right? So it's not really part of Comet, but somehow having this kind of relations somehow can lead to interesting applications and so on, right? Maisa is also saying hello, by the way. Hi, Maisa.
Thank you, Maisa. So, YEJIN, just a comment on this. I think there are lots of explanation relations that you guys with Atomic and Comet and all of this great work that you guys are doing already have there. And I think that we have lots of inspiration on that. And I think that we didn't solve many of the problems that you guys are also saying, oh, we want to focus on that. We are also trying to. So Alias just asked about the negation, and we didn't solve it. So thank you for your comments. And I think this is great job that we can try to keep pushing, because there is so much to be done here. I would like to thank you for your amazing contribution. And we are starting to try to do some of those too here in this different approach. I think we should actually, from my side, I should even work more on how can we complement or finding exactly how complementary knowledge we can generate so that we can try to contribute to. So that's a great idea.
And so in the meantime, YEJIN also checked if atomic-based Comet demo can also handle some of the opinion reactions, and apparently it does.
That's awesome.
So this might be useful, I guess. In the
yes, that's really very useful. And also, let me add here, Marco, the scale. Yeah, so we were discussing scalability before. The scale that we are doing this is really, really not comparable to the scale that we have in Comet, for instance. So because of that, taking advantage of that amount of data or knowledge that is already there and bring it to this context that we have would be very useful, I would say. And I do agree that even though in that case it's not based on opinions itself, But because it has this first, the knowledge base that is built, and then the content that is in BERT, there is some of the content that is there. I told you guys, for instance, that whenever we applied sample, we compared to language models, and in that case, we compared to smaller ones like BERT, yeah, and we found that 15 to 25% of relations we actually extract are new. And many of the ones that we extract are already there. So there is overlap here. It's a very interesting problem to us. We are trying to really focus more on that. How much can we advance in discovering what characterizes those kind of relations that are not learned by the language models, for instance, and how can then we push towards more on that thing? So that's a very interesting point.
Yeah, so we'll have to finish now because we are like 10 minutes over time. As I said, so you had the privilege of the last talk, so we were a little bit more relaxed.
Thank you so much for that, Marco.
Esteban, thanks again. Just to invite everybody for tomorrow's program. So just some of the highlights. I mean, the whole day will be full of talks and so on. But in the morning at 9 o'clock Central European time, we have a keynote on web and, let's say, politics some way by Elena Simperel from King's College. And in the evening, specially invited US audience. So at noon Eastern time and 9 a.m. Pacific time, and 6 o'clock Central European time. It's a panel organized by Ricardo Baeza Yates on AI and ethics, so very popular topics these days, right? And followed by the keynote by Krista Svor from Microsoft on quantum computing. And as the last keynote will be by Ganesh from Carnegie Mellon on very interesting recent paper on future challenges of AI. So Ganesh made similar paper in 1988, predicting how AI will evolve, and he's analyzing his predictions back then. He was pretty good actually doing this back then, and now he compiled opinions on future challenges of AI. And there's a paper in AI Experts in April. So, and he will present results from that paper. So tomorrow will be lots of interesting program. Thanks again to everybody, YEJIN, ESTEVAM, and good night from Ljubljana. I guess you are only starting the day, right? In California. Good night.
Good night. Great pleasure. Thank you so much, Marco.
Goodbye. Thanks.